In previous videos, we've seen how if the leaving group is on a primary carbon, that tells us that the reaction is going to be SN2. If the leaving group is on a tertiary carbon, that tells us that the reaction mechanism will be SN1. But if the leaving group is on a secondary carbon, it depends on two things. It depends on the nucleophile, and it depends on the solvent. Now, in previous videos, we've talked about how a strong nucleophile favors an SN2 reaction, and a weak nucleophile favors an SN1 reaction. And in this video, we're going to talk about the solvent. And you'll see that the reasoning behind the solvent and the influence it can have on a mechanism is actually very similar to the reasoning that we had about nucleophiles. Okay, so what types of solvents can we have, and how would they influence a mechanism? Well, there are two types of solvents. There are solvents that are called protic solvents, and there are solvents that are called polar aprotic. Now the prot here may sound familiar. The prot is referring to proton. And you would have seen this before. A proton is really an H+, really a hydrogen. Oftentimes the word proton and hydrogen are used synonymously, because a hydrogen atom just has one proton in its nucleus. A hydrogen atom is a proton with an electron going around it, and so sometimes the word proton is used synonymously with hydrogen. So protic solvents have a very electronegative atom. So you have a very electronegative atom. This En here is just standing for electronegative, like nitrogen, oxygen, fluorine, chlorine, bromine, iodine, etc., bonded to hydrogen. If you think about the effect of that, think about, for example, water. And actually, let me just make a little more room here. So think about water. Water is a protic solvent. In water, the oxygen is very electronegative. Remember, we need an electronegative atom that pulls electrons to itself, and if it's bonded to hydrogen, then the hydrogens will have a slightly positive charge. Okay, now let's consider. Hydrogens are always on the outside of a molecule because they can only form one bond. So one side will face the inside of the molecule, but the other side will always face the outside of the molecule. So hydrogens are always exposed to the outside world. Now let's say you're trying to do a substitution reaction, and you have a nucleophile. And the nucleophile is prowling through the solution, searching for the electrophile to attack. But as it moves through the solution, it feels the positive charge on all of these water molecules. The water molecules are attracted to the negative charge of the nucleophile, and they all orient in a shell around the nucleus, or around the nucleophile. And so you get this shell around the nucleophile that prevents the nucleophile from ever seeing or attacking or experiencing the electrophile outside of it. Let's say there was a full electrophile over here that it was hunting. The solvent, this protic solvent, surrounds the nucleophile. All of the slightly positive hydrogens face that slightly negative, or face the negative nucleophile and stick to it. It's as if you have a giant that's being taken down by a million garden gnomes. And so in a protic solvent, you disarm the nucleophile. Protic solvents surround and disarm the nucleophile. So imagine, what mechanism is disfavored by weakening the nucleophile, disarming the nucleophile? The SN2 mechanism. Because if you look at the rate law, only the SN2 mechanism has the nucleophile in its rate law. Only the SN2 mechanism is affected by the power of the nucleophile. If you take the nucleophile out of action because you're surrounding it by solvent molecules and it has to push them all off of itself before it can attack the electrophile, then you slow the rate of the SN2 reaction. And if these two are competing, as they are in the case of a leaving group being on a secondary carbon, then by weakening that nucleophile, you're creating a preference for an SN1 reaction. So that's our first principle. If the solvent is protic, then it favors an SN1 reaction. Any protic solvent. Any protic solvent will surround a nucleophile, disarm the nucleophile. That'll slow down the rate of the SN2 reaction and favor the SN1 reaction. So protic solvents favor the SN1 reaction. Okay, well, the other type of solvent are polar aprotic solvents. Now, this polarity is still coming from differences in electronegativity. So you still have, an electronegative atom, something like nitrogen, oxygen, fluorine, chlorine. But it's not bonded to hydrogen. Now, what difference does that make? Let's think about something like dimethyl sulfoxide. This is called DMSO, dimethyl sulfoxide. You have two methyl groups, so dimethyl sulfoxide. Okay, well, in the case of DMSO, you have a really electronegative atom. You have this oxygen pulling electrons to itself, and so you still get a slightly positive charge, but notice that the thing it's bonded to is in the inside of the molecule. Here, in a protic solvent, because it's bonded to hydrogen, the hydrogen is always on the outside of the molecule. The positive charge is always exposed to any nucleophile in the solvent. But if the solvent is polar aprotic, then the positive charge is buried in the middle of the molecule. And now, if a nucleophile is trying to move through the solvent with its negative charge, it's protected from the positive charge of the solvent because the positive charge is in the middle of the molecule. It's buried there. So the nucleophile can just whisk right past this. It barely feels the positive charge at all. And it can jump straight to the nucleophile, to the electrophile that you want it to attack. You're paying no attention to the solvent molecules because the positive charge that would normally slow it down is buried in the middle of the molecule. So that's the case with polar aprotic solvents. Polar aprotic solvents, and here, it's just a word about this name. Polar, they're called polar because you have electronegative atoms. You have big differences in electronegativity, so you have these two ends of these bonds, these positive, slightly positive and slightly negative ends. And that's where the word polar is coming from. You have poles, positive and negative poles on these bonds. Aprotic, though, that means not, the A there means not. For example, if something is not typical, it's atypical. That's not bonded to hydrogen. That's what the protic is referring to, hydrogen. So you still have electronegative atoms. They're just not to hydrogen. It's polar aprotic. Polar aprotic solvents let the nucleophile alone. They don't surround the nucleophile. I mean, they surround it. They don't stick to the nucleophile. They don't form these disarming shells around the nucleophile. They just let the nucleophile do its thing, pushing its way past them. And because of that, because they let the nucleophile be strong, they allow a strong nucleophile to increase the rate of the SN2 reaction, and they favor the SN2 reaction. So, polar aprotic solvents favor in SN2 reactions. Now, if they draw the molecule out for you, you should be able to tell whether it's protic or polar aprotic. You'll recognize protic solvents because they'll have a hydrogen bonded to an electronegative atom, either oxygen or nitrogen. So examples of protic solvents are water, methanol, ethanol, acetic acid, ammonia. And those are very common. Examples of polar aprotic solvents are dimethyl sulfoxide, which we just saw, and all of these other ones. Now, you really should know these, especially acetonitrile. You'll see that a lot in actual chemistry labs. DMF is really common too. It's really best to know all of these. If you ever get stuck, though, if you're pressed for time and you don't have time to memorize these maybe right now, because you'll eventually have to if you're taking the MCAT or the DAT, why not do it now when it'll count for the test too? But let's say you're pressed for time, or maybe you're taking the MCAT and you don't remember exactly what you're learning right now. One little trick that'll probably serve you around 75% of the time is that polar aprotic solvents often have these like alphabet soup names: DMSO, DMF, HMPA. So if you see those and you have to guess, then you could say that you could guess that those are polar aprotic and they favor an SN2 reaction. So we can use this information, the information we have in this discussion, to look at each of these solvents and figure out whether if these were the solvents, they would favor an SN1 or SN2 mechanism. In this first one, we see a hydrogen bonded to an electronegative element, oxygen. So that is protic, and so it favors an SN1 mechanism, because the OH will be exposed to the solvent, the nucleophile. It'll form shells around it. So just for reference here, it's protic, and so it favors an SN1 mechanism. Here we have DMSO, dimethyl sulfoxide. You can see you have the oxygen, but it's not bonded to hydrogen, so it's polar aprotic. Well, that favors an SN2 mechanism. Here we have a hydrogen, and it's bonded to an electronegative element. So that's protic. Protic solvents favor an SN1 mechanism. So this is vinegar. If you do a reaction in vinegar, it's going to favor an SN1 reaction, a substitution reaction. Here we have these electronegative elements, but they are not bonded to hydrogen. So this is polar aprotic. And that favors an SN2 reaction. Here we have a hydrogen bonded to an electronegative element, the oxygen, so it's protic. That favors an SN1 mechanism. Here we have an electronegative atom, but it's not bonded to hydrogen. It's bonded to a carbon, so that's polar aprotic. That's acetonitrile. That specific molecule, very common solvent in laboratories. Polar aprotic, that favors an SN2 mechanism. HMPA, they don't have it drawn for us, but that's one of those alphabet soup names, and so that's polar aprotic. Buries the positive charge in the middle of the molecule, leaves the nucleophile alone, and so favors an SN2 reaction. And finally, in this last one with ammonia, we have an electronegative atom bonded to hydrogen. So that is protic. And a protic solvent favors an SN1 reaction because it disarms the nucleophile. So if you're trying to use the solvent to decide whether the mechanism is going to be SN2 or SN1 in order to correctly predict your products, just make sure what you want to remember is that if the solvent is protic, it's going to be SN1, and if the solvent is polar aprotic, that will favor an SN2 reaction. And you know the solvent is protic if you have a hydrogen bonded to an electronegative atom in the solvent, and it's polar aprotic if you have an electronegative atom, but it's not bonded to hydrogen.